So for question 5, we're explained that if we have a polynomial and we have the characteristic polynomial, when we apply p to that matrix, we get 0. And we want to extend this idea or talk about this idea in terms of linear transformations. And the first thing that we're going to show is that if we have a polynomial, whatever the polynomial is, and it doesn't matter what the polynomial is, in this case, we can use the specific one, but we'll first do the specific one, then do the general case. And what we're going to show is that we're going to show p applied to that lambda is an eigenvalue for t of lambda. So we want to show that for a, if t of x equals lambda x for some non-zero x, then pt of x equals p lambda of x. And first we're going to do it if p equals p of x equals x squared minus 3x plus 2. Then we're going to do it for a general polynomial. So first doing p of x equals x squared plus 3x plus 2. Well, p of t equals t squared minus 3t plus 2i. Thus, p of t of x equals t squared minus 3t plus 2i applied to v, which equals t squared of v minus 3t of v plus 2i of v, which equals t of v minus 3t of v plus 2i of v, which equals t of lambda v minus 3 lambda v plus 2v, which equals lambda squared v minus 3 lambda v plus 2v, which equals lambda squared minus 3 plus 2v, or minus 3 lambda plus 2 of v, which equals p of lambda v. And at some point I switched right here, I switched from x to v. So let's just keep this as v's and v's because I've got a polynomial using x. So we're going to convert all of these to v. So I showed it's true for this polynomial. Now I'm going to show it's true for a general polynomial. So p of x equals the sum of I equaling 0 to n of ai x. And p of t equals the sum of I equals 0 to n of ait, and p of lambda equals the sum xi ti equals the sum of I equaling 0 to n of ai lambda to the I. So p of t of x equals sum of I equaling 1 to n of ai t to the I applied to x, which equals the sum of I equaling 1 to n ai ti x by definition of addition equals the sum of I equaling 1 to n of ai lambda I the x as t of lambda equals, or t of x equals lambda x, which equals the sum of I equaling 1 to n of AI lambda I x by definition of addition, which equals p lambda of, and this should be what we can do of x. So I've shown that x is an eigenvector of this expression. The one thing I used is that if t of x equals lambda x, then t to the n of x equals lambda to the n x. And this is going to be left as an exercise. Now, sorry for jumping back and forth between x's and v's. Hopefully, this is not too hard to follow. Now, the next thing we're going to look at is if t is diagonalizable, then the characteristic polynomial of t applied to lambda, if we look at the characteristic polynomial, then t applied to that characteristic polynomial will be the zero transformation. Using A, we know that the characteristic polynomial of t applied to v equals the characteristic polynomial of lambda applied to v for all eigenvalues. Additionally, lambda of t applied to lambda equals 0 for all eigenvalues. Thus, lambda of t of v equals 0 for all eigenvectors of t. So this is the key of the argument for part B. But why? Well, we need to use the fact that all the eigenvectors give us 0. But as t is diagonalizable, there exists a basis of eigenvectors. Thus, v equals the sum of I equaling 1 to n to ai vi, where vi is an eigenvector for all I. Thus, or then, v equals the sum of I equaling 1 to n of ai, or that's not quite the argument I wanted to go with. Then characteristic polynomial of t applied to t of v equals the characteristic polynomial of t applied to t of the sum of I equaling 1 to n of ai vi, which equals the sum of I equaling 1 to n of ai characteristic polynomial of t applied to t of vi, as characteristic polynomial of I applied to t is a linear transformation, which equals the sum of I equaling 1 to n of ai times the 0 vector, using this argument we had above, our key argument. And this equals the 0 vector. As this is true for any v, in B. T, or the characteristic polynomial of T applied to T equals the 0 transformation. And this is our proof for B.